Hi, my name is Rosti, and today I will present MolSieve, a progressive visual analytics system for molecular dynamics simulations. What is molecular dynamics? Molecular dynamics simulates systems to get a better understanding of their behavior. This is typically performed in groups of related simulations, called ensembles. We simulate molecules to understand how they react to certain situations and conditions. With today's technology, these simulations have grown to be exascale in size. An exabyte is 1 billion gigabytes. This dictates the need for tools for analysis. I was tasked with helping scientists analyze nanoparticles, which are commonly used in manufacturing electronics, textiles, adhesives, etc. The nanoparticles simulations we wanted to analyze were generated by Perez, a simulation management system that can generate very long simulations using cleverer parallel slicing techniques. Perez typically generates systems that are very small in size, only in the order of hundreds of atoms, but with millions of time steps. Unfortunately, these simulations are often subject to the heterogeneous energy barrier problem. This is illustrated by the figure on the right. This is the potential energy surface of a simulation. The black line represents the trajectory, or the path that the molecule took along the energy surface. As you can see, the trajectory spends a long time in the basin before jumping over to another. The transition between spots in the basin do not take a lot of energy, so they happen very often, while transitions between basins occur rarely because of their high energy cost. Scientists are interested in these rare transitions because this is where molecules typically change their shape, which is particularly important for nanoparticles where the shape is highly influential on its physical properties. So, to find these high energy transitions, we developed MolSieve. MolSieve helps find these high-energy transitions hidden within large simulations. This is done using a data reduction scheme. Once the data is processed, analysts are free to view regions of interest that were detected in detail and compare them using various interactions. To understand how MolSieve works, we need to understand how we represent molecular dynamics simulations in memory. A trajectory is a sequence of states, a state being in a unique atomic configuration, and this can be seen in the figure to the right. This 3D representation of a nanoparticle is one of many forms that it can take throughout a trajectory, and as discussed, it tends to repeat. States contain metadata as well as pointers to atoms which contain position information, as well as many other types of data. All of this is stored in a graph database as a graph of graphs, which can be thought of as a hypergraph. Before loading a trajectory into MolSieve, analysts must define the properties they want to study. This can be done using Python scripts. MolSieve exposes atomistic simulation environment representations of a system to the scripts. For instance, we were interested in the common neighbor analysis counts for nanoparticles. These counts characterize the structure and shape of a given particle. MolSieve takes these definitions, calculates the properties, and renders them within its interface. All of this is done on the fly, so analysts do not have to wait for a property to finish calculating to use the system. We use generalized Peron cluster-cluster analysis to simplify the trajectory so that we only focus on its important parts. To do this, MolSieve builds an n-by-n transition matrix that describes the probability of moving from state A to state B. Then, GPCCA clusters states based on the eigenvectors of that matrix and returns cluster membership values, which give the probability of a state belonging to one cluster versus another. Then, we apply a simple threshold. States with cluster membership values below the threshold go into transition regions, and states above go into superstates. This is done because states with a low cluster membership probability are likely to be between clusters, and regions above are likely to be low energy transitions. It should be mentioned that the simplification threshold is an adjustable parameter within MolSieve's interface. This is a trajectory component, which maps directly to a trajectory that we have loaded into MolSieve. The timeline view allows analysts to adjust the detailed statistical views they want to see. The statistical views are divided into horizontal partitions, where each partition corresponds to a user-defined property. Each superstate and transition region is positioned horizontally according to the order in which it occurs in the trajectory, and are positioned such that it is easy to make comparison between both types of views. Superstate views give analysts an idea of the distribution of the property within a superstate. This is done to save space, as superstates typically contain many states. In a transition region view, each property is rendered with the control chart, with anomalous regions being highlighted. Transition regions correspond to those regions with high energy transitions, and the control charts let analysts know what happened to the property they were interested in during the high energy transition period. At the bottom of the transition region view, the state space chart gives analysts an idea of the states within each segment of the transition region. The region is divided into 10 segments, each segment containing the states that occur the most within it. This way, analysts can determine where the trajectory has a lot of movement versus regions that are relatively stable. Finally, several interactions affect the state detail widget, which displays a 3D representation of the state that is being interacted with. These 3D representations can be adjusted in the interface with user-defined scripts. This shows the way that analysts can use MolSieve to select regions of interest within transition regions. The context of the selection are shown at the bottom of the screen in a subsequence view. Once analysts find a region they are interested in, they can use additional interactions to run the nudge elastic band calculation to confirm whether the region is a transition region. The nudge elastic band gives analysts the amount of energy a transition needed to occur. This showcases the various comparison interactions available in MolSieve, which make it possible to compare various regions with one another. This is very important when comparing multiple trajectories. Using the Compare Regions button and clicking any two regions renders a view which makes it possible to compare distributions side by side. The Find Similar Regions button shows which regions are similar within the trajectory in the timeline view. Analysts can generate multivariate charts from the properties loaded into the system. They can also cluster all of the states shown on the screen together using the Cluster States button to find states that are similar across trajectories. Finally, subsequences can be compared using the Compare Subsequences view. We used two case studies to evaluate MolSieve. We will focus on the nanoparticle case study, where we were able to find two sets of transitions that were remarkably similar between two huge simulations, the simulation on the top having 18 million time steps and the simulation on the bottom having 13 million time steps. We found two pathways where the nanoparticle moved from the shape to the left to the shape on the right. The two transparent 3D views are visualizations of the CNA counts within each nanoparticle. This table showcases the scalability of our system. We found that MolSieve scales with the number of unique states, rather than the number of time steps within each simulation. This is logical because the main bottleneck is GPCCA. Finding the eigenvectors of a 500 by 500,000 matrix will naturally take longer than a 50,000 by 50,000 one. Despite the number of unique states, we were still able to load the trajectory in a reasonable amount of time. And that concludes my presentation. I'd like to acknowledge the Vader Lab at Arizona State University as well as Los Alamos National Laboratory for providing me with the opportunity to work on this project.